today I'm going to talk about some physics. And the other day, Shantina started his talk saying, we don't have to wait for a non-materialist science. We've had one for 100 years. We just need to take it seriously. And so today I want to talk to you a little bit about just how non-materialist physics is. But before I do that, I want to say something about why I'm here at SAN talking about physics, and not biology or psychology or neuroscience or something else. Why are so many people who talk at SAN about science end up talking about physics? And the reason is simple. It's that physics is a language and a way of thinking that's very, very simple and very, very abstract. And that has kind of a good feature and kind of a bad feature. The bad feature is because the language is very, very simple and abstract, you can't talk about anything in detail. You can only talk about very easy things, very simple things. The good thing about the language of physics is that it's completely general. It applies to everything. So if I talk about a system in physics, then it doesn't matter whether it's a rock or a bacterium or a person or a galaxy or a black hole. The same thing applies across the board. So if you have a result, it applies to everything. And there's no difference in the way it applies. It applies in the same way to everything. Now that's interesting, and that's why I think that so many physicists are so reluctant to say anything about consciousness. Because physics actually has a very well worked out formal description of one of the most important things that consciousness does, and that's observation. And in the language of physics, observation and interaction are exactly the same thing. Now, from that, you can instantly conclude that in physics, every system is an observer. So if you're a physicist and you want to talk about consciousness, you have no choice but to be a radical panpsychist. And I think that scares people. And they get close to that and they say, oh, not going to go there. But if you take things seriously, again, we have a non-materialist science. We've had it for 100 years. But we have to take it seriously in order to really get anything out of it. So today I'm going to talk about space, which is something that we don't hear too much about SAN. We hear lots about people. We hear lots about objects. And various people have talked about the idea that we each inhabit our own universe that is somehow personal to us. And what I'm going to talk to you today about is about how to extend that to space, and how physics almost demands that we extend it to space if we take it seriously. So in classical physics, we have this space that's all around us, and it's sort of a container. And it's fixed, it's completely objective, and it's filled with objects. But none of that actually works when you go to quantum theory, so when you go to 20th century physics. And we'll see why. And I'm going to present a version of quantum theory that's really only about 20 years old, called quantum information theory, and it was developed starting in the 70s, but it's really blossomed in the last 20 years. And the main concept that comes out of it is that physics, or quantum theory as a part of physics, is really not about things at all. It's not about electrons and protons and stuff like that. It's not about things. It's a theory of observation. So quantum theory is actually a theory about what it means to make an observation. And that's what you'll see today. So if I can have my slides. Oh, I need my little slide thing. Here are the goals for this talk. I want to show you where space comes from. And we're going to get there in 4 steps. First, I'm going to tell you what you really need to know about quantum theory to understand it. 1 slide, very simple. Then I'm going to talk about the idea that in physics, all interactions are actually local. So when we talk about quantum non-locality, it's really a bit of a misnomer because interactions are all actually local by definition. And this is the key point. If you understand that, you're going to understand where space comes from in no time. Then I'll talk a little bit about light and a little bit about the holographic principle, which you've probably heard of, which has been talked about lots in this meeting before and in the popular press. So here we go. Quantum theory in a nutshell. Here it is. The key idea in quantum theory is that physical interaction is mutual state change. So if I'm interacting with you, I'm doing something to you that changes your state, that changes something about you. And if we're interacting, acting together, then you're doing something to me that changes my state. And that process is happening simultaneously. And a convenient way to talk about that is information exchange. If you change my state, then for me, I now have some information. I've learned something by you changing my state. And if I change your state, now you have some information. You've learned something by me acting on you to change your state. And so we can think of interaction as information exchange. So that's the first idea underlying quantum theory, that interaction is mutual state change. And I'm emphasizing the mutual, because back in the classical physics days, we had this idea that I could look at something and get information from it. I could observe that, for example, without changing it. Quantum theory says no. Interaction is mutual state change, not one way. No such thing as a one-way interaction, right? That doesn't even make sense in English. Okay. Principle number 2. There's a minimal state change that I can make in you. If we're interacting, then each of us can do a least amount to the other. And that least amount is to answer one yes-no question. So I can give you one fact, but I can't give you half a fact. I can't give you a tenth of a fact or 100th of a fact. I can just give you 1 or 2 or 3 or something like that, but I can't give you less than 1. So there's a minimal amount of information exchange. And in information theory, that's called a bit, the answer to one yes-no question. So if interaction is information exchange, and there's a minimal amount of information, there has to be a minimal amount of action, a minimal amount of interaction. Okay, that's called h-bar in physics for historical reasons. It's Planck's constant. So quantum theory gives us a minimal, finite interaction that corresponds to transferring 1 bit. And from this, everything else in quantum theory follows. All the fancy math is just a way of describing, asking questions, and getting answers. But this is it. If you understand this, you understand everything that's going on in quantum theory. Right? Okay, so let's go on now and talk about interaction. And here's the traditional picture of interaction. So this isn't the traditional classical physics picture where interaction is one way and nothing makes sense at all. This is the traditional quantum theory picture where interaction is two-way. So we've got 2 systems. In physics, they're always called Alice and Bob. So these are Alice and Bob. They're interacting and they're exchanging information. And they have detectors that can move 1 bit back and forth. So 1 or 0. So this is a very simple picture. They interact by asking each other yes/no questions. So Alice says, what's the weather like? Bob says yes or no, right? And the other way around. And they each have to spend a certain amount of energy to do that. They have to act by a certain amount, and that amount is h bar, or more. But h bar is the minimum that they can do it to get one bit of information. So you'll find this picture talked about everywhere, in every textbook. And the problem with this picture is that it's wrong. It's deeply, deeply wrong. And the key to understanding space is to see how this picture is wrong. So I'm going to spend quite a bit of time trying to show you how this picture is wrong and get you to really understand it viscerally, because it's really a matter of understanding it viscerally, experientially, to see what's going on here. So here's the text version. The traditional picture is wrong. What Alice is really interacting with is her entire environment. And she's not just doing it some of the time, she's doing it all of the time. She can't escape the interaction with her environment. She's embedded in her environment. So why do we think we're interacting with just one thing? It's because we've got an attention system. If you're paying attention to me, you think you're interacting with me, but you're not. You're not interacting exclusively with me. You're interacting with your gut bacteria right now. You're interacting with the atmosphere right now. You're interacting with the chair right now. You may be interacting with the person next to you right now. You're completely embedded in your environment, and that's what you're interacting with. And there's actually a deep mathematical result behind this, which I'm not going to go into. I've talked about it before at this meeting. But it has to do with the way we describe in physics, again, this is all physics, the structure of the world. We describe the structure of the world using mathematics that has the property that you can cut up the world any way you want to, completely arbitrarily, and it makes absolutely no difference whatsoever to the description of your interaction with the world. So I can regard the world as composed of a bunch of people and buildings and tables and chairs and all that stuff, and I can regard the world as one block that has no structure whatsoever, nothing. And the description of my interaction with the world in physics is completely the same. It's absolutely identical in those two cases. So as far as the physics is concerned, there's no difference whatsoever between a world full of objects and a world with no objects at all. It's just the world, and whatever the interaction is, that's it. And I can describe it, and I don't know anything about what's going on in the bigger, wider world. Okay, so let's now look at this as a picture. Sorry, have to do it over there. So here's Alice, and what Alice is really interacting with is her entire environment. And there's no gap, right? She's embedded in the environment, she's interacting with it, and Bob is somewhere in there. But she actually doesn't even know where. Bob is just part of the environment. So she describes the environment as containing Bob. Why? How? How does she manage to do that? She does that on the basis of her interaction with her entire environment. Okay. That's a local interaction, and it's happening at the boundary of Alice. So what's the boundary of Alice? Well, this is where physics is wonderful, because physics gives you a very simple answer. It says, it doesn't matter. You can draw the boundary of Alice anywhere you want to. You can draw it around her body. You can draw it 3 kilometers from her body. You can draw it inside her pineal gland. It doesn't make any difference at all. You can draw the boundary any place you want to. And whatever you've drawn the boundary around is interacting with its environment. You can call that thing Alice if you want to, and you'll change the interaction depending on where you draw the boundary, but you can draw the boundary anywhere. So again, physics applies to everything. You can cut the universe in two anywhere you want to and get exactly the same theory. That's the beauty and also the difficulty of thinking in physics. So all interactions are local. There's no space between Alice and her environment. There's no space between any of us and our environment. The interaction is happening at the boundary that you specify and nowhere else. So to really try to push this home, I want you to all stand up. And I want you to put your hand out like this with your fingers spread really wide and just move it back and forth a little bit, okay? So just enough to feel that there's stuff there, right? We humans are really visual, and vision has totally dominated touch. But when you really try to feel the air, you can feel it. You can feel the fact that you're interacting with this environment. And if you think about your body, right? What's your body? Biologically, your body is just a pipe. And on the inside, there are millions and billions of organisms, bacteria, that are living inside this pipe, which is your body. And you're interacting with them all the time. You're interacting with this air all the time. You're interacting with light all the time. Sound waves all the time. So, you can sit down now. So, what I want you to do is when you leave this room and you walk across the patio next time, imagine that you're naked and you're walking through water so that you can really feel the fact that you're moving through stuff, right? We've been granted these senses that render the air transparent, but that fools us into thinking it's not there. It fools us to thinking that we're living in this vacuum that has objects in it, but that's wrong. We're living in an environment and we're interacting with it all the time. And it's our environment, right? My environment is different from your environment. It's different from your environment. Each of our environments are different by definition, because the environment's just everything but you. So our environments overlap, but they're all distinct. Okay? All right. So let's just try to grasp this and hang with it. Because what this means, if Alice is interacting with her environment, and the interaction is defined right at her boundary, wherever it is, then that interaction can't possibly depend on space. Right? We all learn in undergraduate school or high school or someplace about Newton's laws and action at a distance and all this stuff about bodies interacting and the Earth attracting the moon and all kinds of things like that. And actually, Einstein's greatest contribution to science, the contribution that gave him general relativity, was to say this is nonsense. The interaction is local. What's mass? Mass is the curvature of space. What Einstein did was get rid of the idea of interaction at a distance. He said, interaction's local, it's happening right here, so it must be something about the space right here that is how I'm interacting with the moon. It's not something that's going on somewhere else. So there's no spatial dependence at all. All of Newtonian physics that's written in terms of the force acting on something as being proportional to r squared or something like that, that implies action at a distance. And there's a deep, deep sense in which that's wrong. The interaction is always local, always right here at my boundary, and it's always with my environment. So space disappears when you think of physics like this. You think of a system and another system that's in contact with it, they're interacting, and there's no space in between. So what's space? What is space? What's happened? This is really the key question in what's called quantum gravity, in trying to marry general relativity and quantum theory together. Relativity assumes that space is this big objective thing. And yeah, it's curved. Yeah, interactions are local, but it's still objective. And we've just erased that objectivity altogether. So there's no such thing as objective space. It doesn't exist. So what's going on? Why do we have anything that even looks like space? And I put this slide up about Bell's theorem. You've probably all heard about Bell's theorem. Paul talked about it a little bit yesterday. Bell's theorem says that entanglement is real. quantum entanglement is real. So the Chinese have satellites that can broadcast beams of photons to 2 different cities, and those photons are entangled. So if you do an experiment in Beijing, then you completely determine what's going on at an experiment in Delhi. That's entanglement. So doesn't that show that physics, in fact, is not local, that there are interactions happening that can't be described locally? And that's what almost everyone believes, that this shows that physics is non-local. But when you think about it, there's an experimenter in Beijing that's interacting with their environment. There's an experimenter in Delhi that's interacting with their environment. Those environments overlap. And at least in quantum theory, when you talk about the environment, it's one big entangled mess, right? There's nothing happening in there. There are no objects. There's no dynamics. It's just one big entangled state. So, yes, entanglement is real. Absolutely. But you don't have action at a distance. If those 2 experimenters want to figure out that they've interacted with an entangled state, they've got to get together and talk to each other. So there has to be local information exchange between those observers. And the whole use of entanglement technologically completely depends on people being able to talk to each other. So it's not a purely quantum effect. Everyone says entanglement, just quantum mechanics. No, it requires this communication step that's not described by quantum theory. Or if it is described by quantum theory, it's just described as an interaction. Okay, so Bell's theorem basically says there's no such thing as what's called counterfactual definiteness. Counterfactual definiteness is the idea in classical physics that the moon is there when no one's looking at it. And that there are lots of objects. Each object is in a particular state all by itself, whether anyone's looking at it or not. Now, clearly that picture is completely inconsistent with everything I've told you. There's no such thing as objects out there that are independent of people looking at them. All there is interaction between systems, and systems are defined completely arbitrarily. So again, quantum theory isn't about stuff. It's just about observation. Okay, so Bell's theorem is not an issue. Entanglement is real, and counterfactual definiteness is wrong. And that's it. Okay, so the state of the environment, as far as I'm concerned, the state of my environment is just its answer to a question I've asked. And so I can treat that state as just a binary number. I ask a bunch of yes-no questions, I get a bunch of yeses or nos, and that's just a number as far as I'm concerned, and I say, okay, that's the state of my environment. Now, of course, we are all asking our environment thousands at least of questions per second, more like trillions of questions per second. The time it takes your eye to respond to a photon is in the 100 femtosecond range. So that's about 10 to the minus 13 seconds. So per second, you're asking, in fact, about 10 to the 13th questions. So you're overwhelmed at all times with information from your environment. Much, much, much more information than you're ever aware of. In the ordinary sense of awareness that we talk about when we're trying to get from here to there without running into things. Okay. So that's how we think of this state. And I get that state information by acting on my environment and spending at least h bar per bit. Okay, so now let's ask the question. I've described this interaction as information exchange. Thank you. How does it happen? And physics, again, provides us with a very general theory of how it happens. We just have to take it seriously. So let me give you a very quick idea of what that general theory is, and then we can talk briefly about what it means to take it seriously. So, the first step in this general theory of what an interaction is to ask, what carries the information? If I'm giving you information, if I'm changing your state, how do I do it? And physics has an answer. And the answer is light. At least in quantum theory, light, photons, is defined as the carrier of information. That's what light is. It's how you get information from here to there. And many of you will have seen pictures like this. This is a Feynman diagram. Most of you, how many of you have seen Feynman diagrams somewhere? The popular press, at least. So what this shows is a process that's going on around us all the time, 24 hours a day, regardless of where we are or what we're doing. It's a process in which a neutron, called N here, is happily going along, and it runs into something called a neutrino, which is this eta, and they exchange a photon. They give each other some information. In fact, they give each other one bit. And what happens as a result of that is that the neutron turns into a proton, which is, in quantum theory, is just a vector that points that way goes to a vector that points that way in an abstract space. So the neutron turns into a proton, and the little neutrino turns into an electron. That process is called beta decay. So every now and then, carbon-14 turns into nitrogen-14. A neutron flips to a proton. But this is the role that light plays in all of quantum theory. It's always the carrier of information. So if I give you information, we're actually interacting via light. We're interacting via a photon. And we may sense it by saying, I'm touching you, I'm talking to you, you know, you're smelling something, you're tasting something. But deep down at the level of the physics, what's happening are photons are moving around. And in very, very rare cases, heavier things that act a lot like photons are moving around. But that only happens down at sizes smaller than an atomic nucleus. So now, let's pursue this a little bit further and bring in relativity theory and ask what else is light, okay? In relativity theory, light is defined as, this is not an experimental result, this is a definition. Light is defined as the relationship between space and time. So, now we have an interesting thing. If we want to marry quantum theory with relativity theory, then we have an inference, which is that the carrier of information is identical to the relationship between space and time. Now, we already know that interaction takes time, right? Interaction takes time and energy. So we now have a way of creating space out of the exchange of interaction, because light carries information. Light is what interaction is, and light relates the time it takes to do an interaction to space. And here's how it does it. It does it via the holographic principle, which is a deep, deep principle that people came up with in the 70s to try to understand black holes. And it's typically stated as, you can't get any more information out of something than is stored on its surface. But what the principle really says is that if you're moving one bit of information with one photon from here to there, you can attach a surface to that. And the surface is 4 Planck lengths squared. That's what the holographic principle actually says. Now, of course, that means that if you're getting information out of a thing, it requires that that thing has a size of at least 4 Planck lengths squared. Planck length is tiny, right? 10 to the minus 35 meters. To get that information through. If you don't have that much space, the information can't get through it. So the holographic principle is actually a fundamental principle of physics that links space to information flow. Okay, so almost done here. Alice interacts with her environment. The amount of information she can get from it is determined by the size of her boundary in Planck units, because there's a minimal size associated with getting information from here to there. So the space that composes Alice's boundary is very, very thin. It's only a Planck length thick, but it's got a lot of surface area to allow her to get information through it. So here we are. We create space by making observations. Space isn't there objectively. We interact with our environments, and doing that interaction creates some space. We all live in different spaces. All observers have different kinds of spaces, so space for a bacterium is completely different from space for us, but it's constructed in exactly the same way by the bacterium making measurements. We can share space because we can communicate, and communication is magic. Physics does not have a good theory of communication. You have to build it in from the ground up by specifying how measurement operators work. And you can do it formally, but you're putting that stuff in, as it were, by hand. So I'm just going to give you one bonus at the end. Ask, who makes the most detailed measurements in the universe? Who can get more information out of the universe than anybody else? Who's the biggest learner of everything? And again, physics has an answer. It's a black hole. Black holes are the informationally maximal objects in the universe. Their sizes are exactly given by this formula. The amount of information storage capacity is equal to their area divided by 4 in Planck units. So if I was a black hole, I have a surface area of about 1 meter squared. If I was a black hole, I'd have about 10 to the 70th degrees of freedom. So the number of states I could occupy would be about 2 to the 10 to the 70. 10 to the 70th is about the number of particles in the universe. So black holes have enormous numbers of degrees of freedom. And if you think of me, and you think of my degrees of freedom in terms of number of synapses, it's about 10 to the 15, tiny. If you add 1 million degrees of freedom per synapse, like Stuart Hameroff might want to do, I'm still nowhere near a black hole. Black holes know more about the universe than anybody else. So that's it. Thank you.